Hi, and welcome to Physics 2211 Lab 2. This will be the table of contents for my lab report. The purpose of this lab is to analyze the observed position of an object undergoing projectile motion and compare it to data from a computational model. The object we are analyzing in this lab is a paper ball. Tracker software was used to observe the position of the ball, and this data was then compared to two computational models, one including drag and the other not including drag. Beginning with some key principles, Newton's second law states that the net force equals to a change in momentum over a change in time. Newton's second law can then be used to derive the velocity update formula, where the final velocity vector is given by the initial velocity vector plus the acceleration multiplied by the discrete time step delta t. We also have the position update formula, which will be used extensively in our computational model. The position update formula shows that the final position vector is given by the initial position vector plus the average velocity vector multiplied by time step delta t. The force of gravity is given by minus mg in the y direction and can be assumed to be constant near the Earth's surface. Here, m is the mass of the object and g is the acceleration due to gravity. We will also be looking at the drag force. As objects move through the air, they collide with air particles, resulting in a drag force that slows them down. The drag force points opposite to the object's velocity and is proportional to the square of the speed. In the equation listed at the bottom, b is the constant of proportionality. For the experimental procedure, a video was first recorded of a paper ball being thrown horizontally from a certain height above the table. This video was then imported into Tracker, and the ball's position was tracked frame by frame. Next, a computational model of the ball's trajectory was created in GlowScript, which included and excluded drag. Finally, the data from both the computational model and the tracker software was then used to create a spreadsheet of data to compare the observed and predicted positions over time. However, we had to make several key assumptions when creating the computational model. It was assumed that there was no parallax error when filming, that the ball could be taken as a single point mass, that there was no movement other than in the x and y axes, and that the ball was under constant gravitational force downward. After comparing the actual and predicted trajectories, I saw that the computational model without drag predicted a parabolic trajectory, which ended up overestimating the actual distance that the ball traveled. The computational model with drag, however, underestimated the actual distance that the ball traveled. For the tracker analysis, this is the experimental setup where the ball was thrown horizontally starting at position 0.764 meters above the table. Here, the ball is made from a single piece of A4 paper, which was taken to be 5 grams. Here, the system we are analyzing is the paper ball. The surroundings consist of everything else, including the table and air. Tracker software was then used to track each individual position at each frame, as shown in this clip. When creating the computational model, the mass of the object was set to 5 grams, and the initial position was set accordingly. The initial velocity was then calculating the positions at 2 subsequent timestamps, which gave the initial speed to be 3.33 meters per second. The coefficient for drag was then set to be 0.002. The simulation was then set to simulate for 0.367 seconds, which is exactly how long the tracker data lasted for. The net force was first calculated by determining the force due to gravity and then defining the drag force to be minus b multiplied by the magnitude of velocity squared multiplied by the unit velocity vector. The drag and weight force were then added together to give the net force. The ball's velocity was then updated using the velocity update formula, and this updated velocity was then used to update the ball's position using the position update formula. This is a plot of the predicted positions along with the observed position. The predicted trajectory without drag is shown in green and shows a parabolic shape. However, it overestimates the distance that the ball actually travels. The predicted model with drag is shown in brown and actually underestimates the distance that the ball travels. Here we can see that the actual trajectory in red of the ball lies somewhere in between the two predicted trajectories. The fact that the model without drag overestimated the trajectory of the ball speaks to the fact that the drag force must have come into play. However, the model with drag underestimated the trajectory of the ball, possibly meaning that the coefficient of drag was set too high. Possible sources of error include parallax error when filming the ball's movement, which could cause some inaccuracy in the measurements of the ball's position. Though the ball may have also been given some z component of velocity, which again would affect our measurements. There are also limitations in the frames per second captured by the camera. This resulted in the ball being blurred and stretched in the video, making it difficult to pinpoint the exact center of mass of the ball in the tracker software. Some questions to answer are, do any of the models predict terminal velocity? The computational model that includes drag does in fact predict terminal velocity if allowed to simulate for long enough time. From the graph, we can see that when allowed to fall for at least 1 second, the y position versus time graph appears to approach a constant negative gradient, thus indicating a constant velocity and net zero force in the y direction. This is because the drag force exactly cancels out with the weight force, hence why the ball will reach terminal velocity because it cannot be accelerated downwards any faster. Another question is, if the ball were thrown straight up with the same speed, would the time it takes to reach the ground be the same? The answer is no. It will actually take longer, as the time to fall depends on the ball's height above the ground. By throwing the ball vertically, you are increasing its height above the ground, thus resulting in a longer time to reach the bottom. This is shown by computations where over the same time, the ball has a high Y position than if the ball were thrown horizontally, thus indicating that a vertically thrown ball would take longer to reach the bottom.